saying is that if you come across a polynomial out in the world, whatever its degree is should match the number of solutions. Remember, we talked about that before, and I said it was like being an accountant. So you need to look at it and see what the biggest degree is, and that's how many solutions you should have. That's what this is saying. The reason that it has this kind of crazy jargon in here is because we need to kind of make it for anything, right? Like we could have any power, and so that's what the n is trying to represent, is that it could be the 5th power, it could be the 20th power. But what we know to be true is that if it's degree 20, then there should be 20 solutions. If it's degree 5, there should be 5 solutions. So basically, this is when I've talked about being an accountant, you can think of this as the accountant rule. So if you look at this and you're like, this makes no sense, then you can write yourself a note at the bottom. This is Ms. Bessel's accountant rule, that you need to basically go back and make sure you have the same number of solutions as the degree. Does that make more sense now? Okay, again, typically with math, the notation is trickier than what it's really trying to say. All right, I'm going to have you do another write it down, and then I'm going to explain it sort of moment. Okay, let's start with just this. And this doesn't say location. This has one occasion. I just read it myself, and I was like, location? What was I trying to write? One occasion. So a multiplicity, and a couple of you said it that you didn't remember on the homework, right? That I was writing the answers and you're like, oh, I forgot about the multiplicity thing. We're coming back to it today, okay? So multiplicity is when a solution works for more than one occasion, meaning you factor something and it factors into x plus 3 and x plus 3 again. If you have the same parenthesis twice, then negative 3 is a solution twice. And the way that we word that is negative 3 with a multiplicity of 2. So here's an example, almost identical to the one I just rattled off. So if you come across something and when you factor it, it factors into the same thing twice, that means that negative 3 would be a solution for both sets of parentheses. If it's a solution twice, that's when we get that multiplicity thing. And I'll tell you again how I abbreviate it, because writing out multiplicity 20 times is kind of obnoxious. So I'll tell you how I tend to abbreviate that as well, so that you have a little bit easier way to write it. So we're front loading with a lot of information, but again, a lot of the stuff that we're doing today is going to remain the same with what we've been doing, where we're trying to factor stuff down and we're trying to solve. All the problems that I give you today in class and on the homework are all factorable. So you should be able to factor everything that comes your way. However, remember that you can always set stuff equal to 0 and solve. And if it's quadratic, you can always use the quadratic formula. So there are options if factoring is not the best for you. Okay, did we get all that written down? Okay. Before we continue on, there's one other thing I want to do, and that's talk about some new factoring methods that are all a variation of difference of squares. And I don't know that these are actually methods or if they're made up methods. Like, I almost want to give them names like Batman or something, because I feel like, you know, this is my opportunity to name things. We've done difference of squares, yes? You can also factor a sum of squares. So I want to show you this one. So if you come across something and you're like, oh, I can almost do difference of squares, but it's a plus. The way that we factor those is we get an I in both sets of parentheses. Here's why it works. If I multiply this out, I'll get x squared. I'll I'll get 10ix minus 10ix. So what happens to the middle term if I have that? Yeah, it cancels out. Boom, gone. And then 10 times negative 10 is negative 100. I times I is I squared. Do you remember what the I squared does? It does. So that's why this becomes x squared plus 100. So this is the way people always try to like, oh, I can do x plus 10 and x minus 10. It'll be minus 100. So this is the only way that it'll work and get you a plus sign. So this is what I call sum of squares. Or, I don't know, I should get it. Sum of squares. This one I call difference of not perfect squares because, well, that's what it is. Let's say you come across something like x squared minus 5. So it's a difference, but the second thing isn't a perfect square. We can still factor it like a difference of squares with a plus and minus, except we leave the square roots in. Does that make sense? So then if you look at this one and you're trying to solve, what would make this parentheses 0? Negative root 5. What would they make this parentheses 0? Root 5. Does that make sense? We don't love it? Okay. I'm going to leave these on the board, so if you want to take a picture at any point, if you want to add them to your notes, you're welcome to. They will stay up on the board. The last one I've got is a sum of not perfect squares, and that's when you have a sum, you have two things, and it squares, so it's almost like that first one, except, 7 isn't a perfect square. So it's kind of a combo of both those things, where the 7 will be square rooted and you pick up an I. Okay, so we're going to work through some problems right now that are going to have these as examples, and the more practice that we do, the better we'll get. Let's do two examples together. Let's start with the first one. When you are factoring, you always want to look, here, let me get out of the way if you want to take a picture of the board. When you go to factor, you always want to first start to see if there's something in common. So look at example 1A. After, like I said, take a picture if you'd like. Please go ahead. Look at 1A. Always look for something in common. Is there anything in common that I can take out from those two terms? X squared. So let's take out an x squared. If I take out an x squared, because they both have an x squared to give, I'm left with x squared plus 49. X squared times x squared would get me back to x to the 4th. X squared times 49 would get me back to 49x squared. You're going to see a lot of these new factoring methods come up that we just talked about. Do you see how this one is a sum of squares instead of a difference? Okay, so that's on the board. That made the board, right? First of all, I'm going to break apart the x squared into x times x, because truly I want these to have no squares, no cubes, no anything left when I'm done with them. It's almost a difference of perfect squares, but not quite. So for this one, square root of x squared is x. You put in a plus and a minus, just like it's a difference of squares. Square root of 49 is 7. I put in a 7. The only change is that we need this I, because the I helps us get a positive 49 back.
So even though it's plus, we put minus and plus? So
You put a minus and plus, because when you go to multiply it, it'll be negative 49I squared, and then the I squared will change it to a positive 49. Okay, so let's talk about what our solutions are. What would make this 0? 0. What would make this 0? What would make this 0? What would make this 0? Okay, so how am I going to say this, though? What fancy word am I going to use to talk about the fact that it's twice? X equals 0 with a multiplicity of 2, because it's a solution 2 times. If it had worked 3 times, I would say 3. If it had worked 10 times, I'd say 10. So x equals 0, this is my shorthand, with a mult is short for multiplicity, of 2. Then, I also have x equals negative 7i and positive 7i. I have 1, 2, 3, 4 solutions. So the multiplicity makes it count however many times. So if I have a multiplicity of 2, it counts as 2 solutions. So 2, 3, 4. Is that enough solutions if I play the accountant? Yeah. Okay, so I'm done. Let's go over here. Can I take something out that they have in common? Yes. Yeah, let's take out an x. I'm left with x to the 4th plus 2x squared plus 1 equals 0. All right, this is what we call a higher degree trinomial. We've seen these before when we learned how to factor back a couple chapters ago. It factors just like a trinomial, except to get back x to the 4th, I need x squared times x squared. So normally with a trinomial, we need x times x to get back to x squared. But here we've got a higher degree, we've got 4, so we need 2 of these. You play the same game that you do with normal trinomials. What two numbers multiply to 1 but add to 2? 1 and 1. So if I were to FOIL that back out, those two sets of parentheses, I should get back x to the 4th plus 2x squared plus 1. This isn't completely factored because I still have stuff with squares. So again, how do you know when you're done? There are no squares, there are no cubes, there are no 4th powers. Like everything is down to just x to the 1st. All right, so this is going to be x. I need to factor this further. I need to factor this further. If it helps, you can kind of draw some arrows and give yourself a roadmap where things are coming from. So this is going to factor into 2 sets of parentheses. So is this. And then it's still equal to 0. All right. Which one of our new methods is this? It's almost that one, except is 1 a perfect square? So this one would be sum of squares because 1 is a perfect square. So this is going to be square root of x squared is x. We put a plus in one, a minus in the other. What's the square root of 1? 1, and then we put an I with it. Are these two parentheses identical? Okay, so this one's going to be the same. So I can just kind of thieve my answer from the other one. All right, what would make this 0? That's x. That's just hanging out. 0. What would make this 0 if x were? Yeah, negative I. Negative I plus I would 0 out, right? What would make this 0? I. What would make this 0? Negative I again, right? Those are the same parentheses. How about this one? I. Okay, so let's write our solution. X equals 0. Negative I with a multiplicity of 2. And positive I with a multiplicity of 2. How are we doing so far? Are we okay? It's a lot. Okay. Here's another spot where I'm going to have you write it down first, and then I'm going to help you make sense of it. So go ahead. I know, it looks worse than it is. Trust me, I'm going to explain it in just a second. We've got this. Go ahead and write down what I have written in blue pen. So here's the way that I word these answers. I basically call this the buddy system, okay? So I think back to when I was a kid in school, and especially my freshman year. I feel like freshman year was the year I did this more. If I needed to like go do something, like go to the bathroom, go grab an extra drink at lunch, I always took a buddy with me. I never went by myself. Like I needed a buddy, okay? If you can relate to that, you can understand this. Basically what it's saying is, let's say you go to solve a polynomial and you find out that the square root of 7 is a solution. Okay, so let's say we go to solve. So here we are. Oh, our leg is not attached well. We are solving. Here we are going about our business solving. Oh, okay, bye. So here we are. There's an art field trip. If you are going on the art field trip, it's time apparently. Okay, so here we are going about our day solving with our leg awkwardly attached. And we find out root 7 is a solution. Oh.
If you are going to the art field trip, please make your way to the front entrance now. Thank you.
That means that negative root 7 is also going to be a solution. So if you get an ugly square root as a solution, it never travels alone. It's like me my freshman year. I needed a buddy to go places that made me feel better. So does root 7. So any ugly square root travels with its buddy. And its buddy will always be the same thing but the opposite. So these travel together in the buddy system. Likewise, if you are walking along, oh look, my leg's attached better this time. If you are walking along solving, here I come, I'm solving, and you get 3i is a solution. 3i also needs a buddy. If 3i is a solution, then negative 3i also has to be a solution. And the reason that this is true is because we can't get these polynomials with nice coefficients unless we have this buddy system. So the way that I word all this, ugly square roots travel with their buddy. So I always have a weird way of saying it as compared to your book. Your book has this nice, concise way of saying it with numbers and letters. And then Miss Bessel comes along and says, ugly square roots travel with a buddy. So I have my own interesting Miss Bessel way of saying things. So all this is saying is if you get a square root for an answer that's ugly, it's going to travel with its buddy, which is the opposite. And then same thing here. Imaginary solutions travel with a buddy. So again, I kind of call it the buddy system. So if you get ugly square roots or imaginary answers, they travel in the buddy system. And that's all this is saying up here. Again, I'm just saying it in kind of my own Miss Bessel language. Does that make a little more sense? A little bit? Okay. I'll take a little bit at this point. Okay, let's flip. We've got 2 more examples that we're going to try. And originally, I was going to have you do problems out of the book, but I had one of those moments with your textbook again where I went to look at the textbook and see, and I was like, oh, it was something. So I made my own worksheet, and that's what you're going to get today. So you can see how I started to write out like page blah, 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 and then I was like, nope, just kidding. We're going to punt on that. Let's do a worksheet. Okay, here we go. 2 more example problems. And again, this is kind of one of those situations where the more you practice, the better you're going to get. Okay? Let's start with part A. We're factoring again. There's nothing I can take out that they have in common. If there are 4 terms, what's the first thing you think of? Grouping. Okay, so I'm going to group the first 2 and last 2, which is typically what we do, but not always. Do you see how the first 2 have a bunch of x's and the second 2 are both divisible by 7? Do you agree with me? Okay, so let's look at the first 2. Let's pull out an x squared. If I pull out an x squared, what am I left with? X minus 3. look at the second two. What can I take out that they have in common? A 7, and I'm left with what? X minus 3. All right, so I have two things. I have thing 1 and thing 2. Remember, I said I sound like Dr. Seuss at this point. Thing 1 is what they have in common. Thing 2 are the leftovers. Okay, what new factoring method is this one? Which one is it? Sum of squares. So let's use sum of squares. So x minus 3, this one is going to factor into 2 sets of parentheses. Yeah, it is true. You're right. It's this one. And funny enough, it's exactly this one in so many ways. Yeah, it's sum of not perfect squares because 7 isn't a perfect square. Okay, let's start with this. Square root of x squared is? Square root of 7 is what? Just square root of 7 because it's ugly. Leave a little space out front. Do you see how I left just a smidgen of space out front? Remember, you get 1 plus and 1 minus because that's how we get the middle term to cancel out every single time. Do you see that they all have that in common? They're all 1 plus 1 minus, 1 plus 1 minus. Do you see that? It has to happen that way so that the middle term goes away. That's why. All right, now, because it was a sum of squares, anytime it's a sum of anything, even though they weren't perfect squares, I get also the I. So do you see how these two travel together in the buddy system? Again, that's all that last part was trying to say, but it looked more confusing. All right, what would make this 0 if x were? What would make this 0? Negative I root 7. What would make this 0? Yeah, so you're just thinking like you want to subtract it away. We call those additive inverses when they're things that add to 0. So again, if you have imaginary things or ugly roots or a combo of both in this case, they travel with a buddy, always. All right, let's look at the next one. Can I take anything out that they have in common? Yeah, what can I take? Okay, so let's take out an x. I'm left with x to the 4th minus 8x squared minus 9. This one is one of my, I call them higher degree polynomials because it's 4 than 2 than nothing. So I treat it like it's a trinomial. So I get 2 sets of parentheses. Instead of x times x to get x squared, what do I need to multiply to get x to the 4th? X squared times x squared, and that'll get me back my x to the 4th. Okay, I need two numbers that multiply to negative 9 and add to negative 8. What are they? Negative 9 and 1. Negative 9 plus 1, is that negative 8? Negative 9 times 1, is that negative 9? Okay, perfect. All right, one of those is a difference of squares, right? So this will be 2 sets of parentheses, x plus 3, x minus 3. That one's not bad. This one is what from our list up here? Sum of squares. So we're going to do x plus, x minus. But then, because it was a sum of squares, I go to take the square root of 1. What do we know the square root of 1 is? 1. But because it was a sum of squares, what pops up? I. So this is going to be 1i and 1i. You can write the 1, but you don't have to. All right, let's write our solutions. X equals, what would make this 0? What would make this 0? This one. This one. Negative I, positive I. Did my i's travel in the buddy system like they were supposed to? Yeah. I have 5 solutions. How many solutions was I supposed to have? 5. So again, I kind of have my own language and way of explaining things. So again, to me, these are the buddy system. And then the other thing I showed you that looked a little confusing at first was the accounting idea that I always talk about. All right, so we have homework